In this video, we're going to look at the directional derivatives and gradients. So first we're going to start out with finding the derivative. Now we want the partial derivative of my function with respect to x and the partial derivative of my function with respect to y. So we'll find the partial derivative. So the partial derivative of my function with respect to x will be equal to, well, it's going to be 1 over 3x raised to the fourth y squared. And then the derivative of that, which is going to give me 12x cubed y squared, and then plus the derivative of the second term with respect to x is just going to be y squared. Now if I want to find the partial derivative with respect to y, then it will be 1 over 3x raised to the fourth y squared multiplied by 2 times 3x to the fourth y, and then plus 2xy. Now, what we just did was we found the derivative with respect to the x or y axis, and it's a partial derivative. So in other words, what I'm doing is I'm doing a very small increment change, and it is running parallel to the x-axis when I'm doing the partial derivative with respect to x, and the partial derivative with respect to the y is running parallel to with respect to the y. And it's that instantaneous rate of change. And the slope that we're looking at is tangent, the slope of the tangent line is parallel to the x or y axis, respectively to what I was doing the partial derivative of. This idea, of course, can be expanded out when we're doing the partial derivative of my function with respect to z. Most of the time, however, we're not looking at slope of the tangent line parallel to an axis. More often than not, we want to find the slope of the tangent line in a different direction than the axis. And so that's called a directional derivative. So in other words, I'm going in some direction of my angle, and this, I'm going to do it in 2-space first. My angle theta, where theta is defined like we normally would do in pre-calculus 2, which I would start on the positive x-axis and do my regular clockwise rotation. So if I wanted to know what my slope of my tangent line is in this direction, I'd need to know this angle that is referenced off of the x-axis. And I just put this point AB arbitrarily on the xy plane. So that means that the distance we are traveling h in the direction of the unit vector can be given by the cosine of the angle and the sine of the angle in the I and the j direction. Therefore, the z-coordinate up here in space of the second point on the graph is given by z is equal to f of a, where I start, plus some h, small increment of h, cosine theta, b, plus my small h, my increment of sine of theta. And of course, you know what's happening is we're going to be doing the limit. So here's in 3-space, this is what it would look like. Here's my point that I had before. In 2-space, here's my angle theta. And I'm really looking at, this is the direction in which I am looking at the slope of the tangent line in this direction, which you can see is not running parallel to the x or the y axes. Of course, we then talk about the secant line, which is when we're in 2-space, this is f of x plus h minus f of x all over h, which then means we can take the limit of that. And we call this the directional derivative of f in the direction of u. That's the direction we want to go. And this is in terms of my angle off of my positive x-axis. I can then go into 3-space. I can take that idea and bring it into 3-space. And in 3-space, I have the cosines. You know, these are my directional cosines, and this, of course, is a refresher. Directional cosines, I believe, was in section 2.3 in your book when we talked about directional cosines. And then from 3-space, it is the cosine of alpha, cosine of beta, and cosine of gamma, where alpha is off the x-axis, beta is off the y-axis, and gamma is off the z-axis. And of course, we take the limit. That leads us to the definition of the directional derivative in 2-space, which is going to be defined as the partial derivative of x evaluated at some point xy, the cosine of the angle that I'm looking at, and then the partial derivative of my function in the y direction evaluated at the point xy if we have that, and then the sine of theta. Now, we can expand this out into 3 space where my u is going to be the cosine of alpha, cosine beta, cosine of gamma in the ijk direction. So then this vector u ends up becoming, as you can see, it's going to be a dot product. Now, this is where you can find the information in your book. It is in section 2.3, page 161, a refresher on finding the directional cosines and what the definition is. So we're going to start out with a couple of examples. We're going to do it in 2 space, and then we're going to move into 3 space, because 2 space is easier to work with, and then we get into 3 space, and then realizing, of course, everything that we are doing can be expanded out to 3 space. So they're asking us to find the directional derivative of the function at the point P in the direction of u. This is my vector u. So the first thing we want to do is find our partial derivatives in each direction. So my partial derivative with respect to x is just going to be of xy, is just going to be y. And then my partial derivative with respect to y of xy is just going to be x. So I find my partial derivatives. The next thing I want to do is I want to evaluate my partial derivatives at the given point. Or do I have it? Yep, I have a given point. So from here I have my my partial derivative at the point 0, -2, which is going to give me -2. My partial derivative of y at 0, -2 is just going to give me 0. Now they're telling me in this direction, this is my direction theta. So if I were to draw a nice little xy plane here, the cosine of cosine inverse is 1/2. Now we don't know if that is in this quadrant or in this quadrant, except for the fact that it is the arc cosine or the cosine inverse, and cosine inverse is only defined in quadrant 1 and quadrant 2. So we know it has to be in quadrant 1 because that is how cosine inverse is defined. So I look at my unit circle and I say, where is cosine equal to 1/2? Well, that happens when my theta is at pi over 3. So then my u is going to be the cosine of pi over 3, and then the sine of pi over 3. So this becomes cosine of pi over 3, which you already knew was 1/2 I. And then the sine of pi over 3 is square root of 3 over 2 in the j direction. Now, by my definition, my directional derivative, d in the u direction of my function x comma y, is equal to my partial derivative in the x, and then the cosine of my angle theta in the I direction, and then plus, and this should be I hat, so I don't think it's a complex number. And then it's going to be my partial in the y direction, the sine of my angle in the j hat. Now we know what my partial derivative in terms of the x, well, that is equal to -2. So this is equal to -2. And then my partial derivative, or my cosine of my angle is, we know, is 1/2. It's cosine of my angle. And then plus my partial derivative with respect to the y, we know, is 0. And then it's going to be the sine of my angle, sine of pi over 3, which is the square root of 3 over 2. And so my final answer is just -1. Now let's go ahead and do the second one here, where I don't know what my angle is. So for this one, I'm going to do my usual stuff, but this, I know that my u is going to be the cosine of my angle. Well, cosine of my angle in the I direction. The cosine of my angle is 4/5. So how do I find the replacement for the sine of my angle in the j direction? Well, I go back to the way that we define our sine and cosine in terms of x, y, r. Since my cosine is a positive number, and I'm only defined for the cosine inverse in quadrants 1 and 2. That tells me that my r value is 5, my x value is 4, x is equal to 4. That means my y value is 3. The sine is defined, so this is in the I hat. The sine is defined as the y value over the r value, and so it is going to be the 3 over 5 in the j hat direction. So now I found those pieces. So I'm going to go back now and find my partial derivative with respect to x of this. And so I end up with 2xy minus y squared. I'm going to evaluate that at the point -1, 1. So this is going to give me 2 multiplied by -1 multiplied by 1 minus 1 squared, which is going to give me, what is that, -2 minus 1, which is -3. I'm going to do the partial derivative of my function with respect to y of xy, which is going to be x squared minus 2xy. I'm going to evaluate this at the point -1, 1, which gives me 1 minus becomes +2, so it's +3. So now I can jump to my directional derivative in the direction of u of my function of x comma y. We know that this is going to be the partial derivative with respect to x, so that is where the -3 comes from, and then 4 over 5, so 4 over 5, and then it's going to be plus, and then I have my partial derivative with respect to y, which is 3, and then multiplied by 3/5. So this ends up becoming -12 plus 9 over 5, which gives me a final answer of -3 over 5. And that is my final answer. So the directional derivatives in and of themselves are not too terribly difficult because we're familiar with doing partial derivatives and evaluating it. The only extra layer is this direction that we want to go into, the direction u, instead of along the x or along the y-axis. I just want to, these, since after we've done the directional derivative, those, of course, is no longer a vector. Now, if we think about the fact that when I'm looking at the partial derivative of f with respect to x cosine theta and the partial derivative of my function with respect to y sine theta, it looks a lot like a dot product, final kind of dot product, where my vector is the partial derivatives in the I and the j direction, and u is the cosine and the sine in the I and j direction. And if we think of it that way, then really what the directional derivative is just a dot product of the direction I'm going in for u times this thing here, and we're going to call this specifically the gradient. And this little upside down triangle is called the nabla, and it is read, the nabla of f is read as del f. So this upside down thing is the del f, and we're going to call this the gradient. So here's this new word, gradient. And here it is in 2 space, and here it is in 3 space. So if I'm asked to find the directional derivatives of the function at the point in the direction of v, then I can do it by just finding my the dot product of my gradient and my vector. So the first thing I want to do is find my gradient. So I'm going to find my partial derivative of h with respect to, and I wrote f, h with respect to x. And this is going to be, sine of y is just a constant, so this is just going to be e to the x sine y. I'm going to evaluate this, the partial derivative of h with respect to x, evaluated at the point 1 comma pi halves, which is going to give me e to the 1 and then the sine of pi halves, which is going to give me just sine of pi halves is 1, so it's e. I'm going to do the same thing with the partial derivative with respect to y. So here's y. And now e to the x is a constant, so I'm really just doing the derivative of sine y, which is cosine y. So I have e to the x, the sine, I said sine and I meant cosine, the cosine of y. Now I'm going to go ahead and find this partial derivative. So evaluate it at this point, which is going to be e to the 1 still, and I have the cosine of pi over 2. Now the cosine of pi over 2 is 0, so this part is 0. So my gradient then, so my delta f of x, y, is going to be equal to my e in the I direction plus 0 in the j direction. Because remember, this is my partial derivative evaluated, my partial derivative with respect to x evaluated at that point, and this is my partial derivative, that's a 0 there, of my function with respect to y evaluated at that point. And so now I just have to find the directional derivative, which we know is going to be this gradient dotted with my vector that I'm going in. So I have e comma 0. Doing the dot product, my v is just negative 1 comma 0. And so my final answer then, this is my directional derivative, so dv of f of x comma y, is going to be equal to just negative e, and that's it. So let's go ahead and take a look at the next two examples. Now I'm just going to give you the answer for b, and then we're going to walk through c. So the directional derivative of my function, this is just xy, is going to be equal to 5. I want you to walk through that and see if you're getting the same answer as I'm getting. Now the next one's a little bit more involved, and I'm going to set you up and I'm going to have you finish it. So the first thing I want to do, of course, is find my directional derivative of my function with respect to x, which is just going to be z. And then I'm going to evaluate this at the point 1, 2, 2, and we know it's just 2. Find my directional derivative with respect to y, which is just going to be 2y. Evaluate this, dy, at 1, 2, 2, which is going to give me just 4. Now, the last thing we have to do on this one is find the directional derivative with respect to z. And you're thinking, but wait a minute, this is only x and y. Well, yeah, it's only x and y, but I'm given the point x, y, and z, and I'm given a vector that has I, j, and k. So I do have to find this directional derivative with respect to z. And when I find this directional derivative with respect to z, it's just going to give me x. Evaluate it at the point 1, 2, 2, and this is just going to give me 1. So now I've found my gradient. So my gradient of f is going to be the vector 2, 4, and 1. I'm going to find my directional derivative. Now, up until now, maybe even on this one, b, up until now, my directional derivative, I didn't have to worry about finding the unit vector. This one I do. So when we're talking about the directional derivative and being able to do the dot product, the vector that I want to look at has to be the unit vector. Now this is the unit vector. This is a vector of magnitude of 1. And convince yourself this is also a magnitude of 1. This one does not have a magnitude of 1. So before I can do my dot product with my gradient, I do need to find the unit vector in this direction. So to find the unit vector, v, and I think it's v hat as the unit vector, is I have to take my vector, which is 2, negative 1, and 2, and I need to multiply it by the magnitude of v first. So before I can do this dot product, I do need to find my unit vector. And I didn't have to do it on my other ones because they were already unit vectors. Go take a look and make sure you convince yourself that. So I have to find my magnitude of v, and my magnitude of v is going to be the square root of 2 squared plus negative 1 squared plus 2 squared, which ends up giving me, what is that, 4 plus 4 is 8 plus 9, so that's 3. So it's the square root of 9, which gives me 3. And so my v hat is going to be 2 divided by 3, negative 1 divided by 3, and 2 divided by 3. Now, once I have done that, so when you're doing your homework and you're thinking, why aren't I getting the right answer? Make sure that you have a unit vector in that direction of the vector that is given to you. It has to be a unit vector. It's really, really important. Make a note to yourself. To do this dot product, make a note to yourself. This needs to be a unit vector. Not the gradient, but the vector in which you're doing the dot product with. Okay, so now I have found the unit vector, which is 2/3, -1/3, and 2/3. And that should be a 3 right there. And when I get done, my answer should be just 2/3. Convince yourself that's what it is. We get a couple of properties with the gradient here that are kind of important. Now, if we recall from section 2.3, the angle phi between the two vectors u and v uses the dot product, where the cosine of phi is going to be the dot product of u and v divided by each one of the magnitudes. Therefore, the angle between my gradient and my vector that I'm looking at will be equal to my partial derivative times the dot product of u, which is just going to be u cosine of phi. But remember, this is a unit vector. This whole big thing I made up here, unit vector. The magnitude of the unit vector is, of course, going to be 1, and so we end up with this. And from that, we get this bit of information. So if my gradient is 0, now gradient is my vector, then my directional derivative has to be 0 for any unit vector I choose for u. It doesn't matter what u is. If my gradient is u, then my directional derivative is, or if my gradient is 0, my directional derivative has to also be 0. If my gradient is not equal to 0, so these are the two cases where it's not equal to 0, then the directional derivative is maximized when my vector that I'm looking at points in the same direction as my gradient. And the maximum value of my directional derivative will be the magnitude of my gradient. Again, if my gradient is not equal to 0, and my directional derivative will be minimized when u, the vector I'm looking at, points in the opposite direction from my gradient. And the minimum value will be the magnitude of your gradient and then the negative of that. So here's a picture that you can see that in this case, this is my gradient, right? And my gradient will be the most rapid increase would be my gradient in this direction. And then, of course, my gradient in this direction, which is the negative of my gradient, will be the most rapid decrease in my function. So they're asking me to find the gradient, which we have been doing. We've been doing this. We just went further. Now we're just asked to find the gradient. So to find the gradient, this is just finding the partials at each partial with respect to x and the partial with respect to y, and then evaluate it. That's all the gradient is. So I'm going to find my partial derivative of my function with respect to x, which is going to be, I'm just going to jump in there. 14 is a constant, so that's going to go to 0. And then it is negative 2x divided by 3. And then y will be considered a constant, so don't have to worry about that part. And then I'm going to do the directional or the partial derivative with respect to x evaluated at the point 1, 2, which gives me negative 2/3 multiplied by 1. So in other words, negative 2/3. Now this is my I component of my gradient. And then I do my partial derivative with respect to y, which is going to give me negative 2y over 3. I'm going to evaluate this. That's y, evaluated at 1, 2, which is going to be negative 2/3 multiplied by my y, which happens to be 2. So this is negative 4/3. Now that is the multiplier on the component of my j. So my gradient here, my gradient of f of xy is going to be equal to negative 2/3 in the I hat direction and minus 4/3 in the j hat direction. Now this is nothing new. We've been doing this. We just didn't call it the gradient. Now let's take a look at this one. Now this one is asking me for a point in 3 space. So I'm going to have to find the partial derivatives in each direction. My partial derivative with respect to x will be the multiplier in the j or in the I direction. The partial with respect to y will be in the j. And the partial with respect to z will be in the k direction. So my partial with respect to x, my partial with respect to y, and my partial with respect to z. Look at that, I should have had an f there, an f, and then the z. Okay, so with this one, I'm going to do the partial with respect to x, so it's going to be y, and then plus z. The middle term would be considered a constant. My partial with respect to y is going to be x plus z, and then my last term would be considered a constant. And then my partial with respect to z, which is just going to give me y plus x, because my first term would be considered a constant. So now I'm going to evaluate them. Partial with respect to x at the point 1, 2, and 3. So this is just going to be 2 plus 3, which is 5. That is the coefficient in the I direction. My partial with respect to y, 1, 2, and 3 will give me 4. My partial with respect to z, evaluated at 1, 2, and 3, and of course gives me 5. So my final answer then is, well, actually that doesn't, it gives me 3. It's x and y, which gives me 3. My final answer is my directional derivative of f of x, y, and z is equal to 5i hat plus 4j hat and then plus 3k hat. This last one is they're asking me to find my gradient, and I want to have it in the same direction as this given vector. So as before, the first thing I'm going to do is find my partial derivatives and evaluate it. So I'll let you do that, and I'm just going to tell you what the gradient is going to be in the x, y, and z direction. I'll let you do all the work to get there, which gives me 1 over 54, and then it's going to be 4, 4, and 24. This can reduce if you're inclined to 1 over 27, 2, 2, and 12. Now, what they probably want here is the directional derivative, because I found the gradient. The gradient is done. If I want the directional derivative, then I got to make sure that this is a unit vector, first of all. And so I'd look at this and I'd say I've got 3 squared, which is 9, plus 4 squared, which is, that's 16, which is 25 together, and 25 squared plus 12 squared does equal 13. So this is in the unit, this is a unit vector. So I did a quick check to make sure that is a unit vector. And then, so if they want the directional derivative, so d in the direction of u, of f of x, y, and z, then this is just going to be the dot product of 1 over 27, 2, 2, and 12. And the dot product, I'm going to factor out a 13. So I'm going to factor out a 13. And then I have negative 3, negative 4, and negative 12. That just allows me to do the dot product much easier by knowing that all of the rules that we have with the dot product and scalars and vectors, that I can just do the 1/13 times the 1/27. And if inclined, I can actually pull out a negative 13th. But anyways, my final result should be 158 over 351. Check my math on that, and if I had any problems there, go ahead and let me know. Okay. Now, on this, we're going to start thinking about, we want to find the derivative of the function in the direction of the function that increases the most rapidly. That brings in together some of the definitions and theorems that we had up above about gradients going in the same direction as my vectors, or going in the opposite direction of the vectors when I'm doing my directional derivatives. When I'm doing this, the first thing I'm going to want to do is find my gradient. So number 1, find my gradient. So the gradient of f. And this is going to be equal to 2x plus y, comma, x plus 2y. My second thing I'm going to want to do is evaluate my gradient at the point given to me. I'm going to end up with negative 14, comma, negative 13. Now I know that the maximal value is going to be the magnitude of my gradient. So the max value is going to be the magnitude of my gradient evaluated at my x naught, y naught. So in this case, it is going to be the magnitude of -14 and -13. And the end result here is going to be the square root of 365. Now, if I want to know the direction in which this is going to happen, the direction u, then after I found my gradient, then the next thing I'm going to do, if I needed that direction, is I'm going to find the unit vector for my gradient. So I would have my unit vector of my gradient, my vector u, which is going in the same direction as my gradient, which would be 1 over the square root of 365, and then the -14, and then the -13. And this will give me my vector that is going in the same direction as my gradient, and it'll be a unit vector in that direction. Now I can find from there, I can also find the directional derivative by just doing the dot product of these two. But what'll end up happening is when I do the dot product of these two, my directional derivative, the dot product will be the dot product of my gradient and my unit vector in the same direction, which is just going to give me my magnitude. So there is that. I'm going to go ahead and let you do this one, and then I'm just going to pause it. You should pause it so you can put an answer in. And so when you get done with this one, you should have your maximum value should be the absolute value of the gradient, x naught, y naught, and z naught. And hopefully what you all got was the square root of 50 divided by 99, or 5 root 2 over 99 as your final answer. All right, so there is some more things that the gradient gives us. Let's talk about the gradients and what the level curves do for us. So using a tool, the topographical map, the steepest slope is always in the direction where the contour lines are the closest together. So the slope from this point down is going to be a much steeper slope than this point, because of the fact that those are the curves are further apart. Now the slope could be steeper going down, or it could be going up. Depends on what each one of these curves gives us. If the level curves are increasing, then of course the slope would be increasing. And if our level curves were decreasing, then our slope would decreasing. Now, what we get from this is, suppose my function z, which is a function of x and y, has a continuous first order partial derivatives on some open disk centered at the point. And if my gradient does not equal 0, then my gradient is normal to the level curve of my function at that point. And that allows us to talk about the equations of tangent planes and normal lines to the given surface at the given point. So at the level curve, f of x, y, z is equal to 12 for the function, excuse me, sorry, allergies, man. For the function x, y, z, where I have 4x squared minus 2y squared plus c squared at this point, the first thing I'm going to want to do is I'm going to find my gradient. So my gradient is the first thing I'm going to do at the x, y, and z. Now my gradient is going to be equal to, and you all should check this on your own, 8x, negative 4y, and then 2z. Now when I evaluate this at the point 2, 2, and 2, I end up with 16, negative 8, and 4. Now, my normal, then, based on what I know from above, my normal vector is going to be the vector 16, -8, and 4. Now, I can factor out a 4 out of each one of these, so I can work with smaller numbers. It's still going to be a normal, so it's going to be still be in the same direction if I factor out a 4. So I come over here and I factor out a 4, and I have 4, -2, and 1. That means my normal vector I can write as just the 4, -2, and 1, if that, helps me. Now, if we recall from our last section, 4.5, then the tangent equation, remember our tangent equation, is going to be our partials in each direction. So my partials in each direction, which is the 4, x minus my x naught, which happens to be 2, and then minus 2, then y minus my y naught, which is 2, and then plus, and then I have my z minus z naught, which is minus 2, and this equals 0. And this is because this is the a, b, and c. These are my components of my normal vector, which is the partial derivatives in each one of those directions, evaluate at those points. So there is the equation of my tangent plane, so that's nice. Then we have to go back a little ways in our knowledge, and I believe it was in the 2.5 equations of lines and planes in space. So the next thing is they want to find the equation of the normal line. We've got the equation of the tangent plane, that's this. The equation of the normal line, if we remember, goes through this point 2, 2, and 2. And we have this vector n, which is equal to 4, -2, and 1. Then the way that I can write my normal line is with a parametric. Do you remember the parametric? So it would be equal to my x minus 2 is equal to 4t. My y minus 2 is equal to the -2t. And my z minus 2 is equal to t. That's one of the ways that we could have wrote it. The other way that we could have wrote this, if you remember, was in the form of the, let me see, when we have them solved for z, so we could say this is x is equal to 2 plus 4t. Y is equal to 2 minus 2t, z is equal to 2 plus t. And then, of course, the other way that we could write this is the symmetric, where we have, let me see, since we're solving for t each place, so it would be x minus 2 divided by 4 has to be equal to y minus 2 divided by -2, which has to be equal to z minus 2 divided by 2. And then, of course, we can do it also this way. We have this point, which is the point 2, 2, and 2 plus t, and then multiplied by my normal, which is 4, -2, and 1. So there are multiple ways of writing the equation of this line. If you remember from section 2.5, there are 3 different ways of writing this equation of the line. So this is equal to L, and so these are the different ways of writing this. Let's do this last one here, and I'm just going to give you the equation of the tangent, and then the equation of the line. So the equation of your tangent is going to be 1 x minus 1 plus 1 y minus 0 plus 2 z minus 0 is equal to 0. So that's the equation of the tangent. And of course, the equation of your normal, the equation of your tangent line, that's the equation of the tangent plane, the equation of your normal line, is x. This is one of the ways. X is equal to 1 plus t. Y is equal to 0 plus t. Z is equal to 0 minus 2t. So I get x is equal to 1 plus t. X is equal to t. Y is equal to t. And z is equal to negative 2t. And of course, we can also write this as the point, 1, 0, 0 plus t multiplied by 1, 1, and negative 2. And I believe this should be a negative 2 up here as well. So negative 2. Negative 2. Anyways, there's your equation of your line, your normal line. And, oh, and I didn't give it to you in the symmetric way. And the symmetric way would have been x minus 1 over 1, which is equal to y over 1, which is equal to z over negative 2. So that is the different ways of writing the normal line. And of course, we have our tangent plane, which we're very familiar with. I would recommend that you consider refreshing some of your normal line representations, whether you're doing it in the parametric form, the symmetric form, or in this form, to find and it's pretty straightforward if you refresh. Other than that, that's it for this section.